Welcome everyone here and everyone online to another Cambridge RIC seminar. This week, we're delighted to have Sarah Johnston, who is currently a PhD student at the astronomy department in Durham University. And she's going to be talking to us a little bit about the work she's been doing during her PhD, very much with kind of an RIC bent on it, introducing sort of some GPU porting to the Swift cosmology code. Thank you very much.
Awesome. Yeah, hi, thank you very much for having me. It's really lovely to be here. So as Jack said, I'm a fourth year PhD student. So this is quite a chunk of work now that I'm going to try and present in. But the good thing about doing a PhD is the first year of it all goes down the drain anyway. So this is only about 2 years of work. But yeah, I'm based in the Institute for Computational Cosmology in Durham, which is part of our astronomy section where we focus on kind of supercomputing and HPC applications. And mine is very much along the HPC lines. It's really exciting to go talk today and to talk kind of specifically to this demographic, because I spend a lot of my time trying to explain computing to astronomers. I spend more than half of my talks usually explaining how a computer works. So it's very nice to be doing the opposite today and to be trying to explain astronomy to you guys instead. And the especially good news about this talk is you have to have basically no understanding of astronomy to hopefully follow what I'm going to go through today, because the only word that I'm going to mention over and over again is gravity. And that's probably something we're all familiar with from, you know, falling over and falling downstairs and dropping things on the floor and stuff like it. So as a very kind of general overview to start us off, we spend a lot of time as astronomers thinking about our place in the universe. And if you have ever been to any kind of like science museum exhibits, or if you have things like posters on the classroom walls of high schools, you see a lot of things like this, where it shows you a picture of a galaxy and it says like, you are here in space. So this is meant to be a representation of the Milky Way, which is our galaxy. And there's some kind of big arrow to like inspire kids and be like, look how small we are. But actually, when it comes to the work that I do, my version of the universe doesn't look like this. My version of the universe looks like this. So this is something that we call the cosmic web, which is like an overarching structure in the universe. And it's basically the idea that if we zoom out on what the whole universe looks like, this is the kind of structure that we see. So it's called web after like a spider's web, cosmic being universe spanning. And actually all of the bright points that are within a diagram like this represent where a single galaxy is forming. And then we have all of these bright points come together and all these galaxies across the universe that makes the structure that we live in. And you can imagine that with that many galaxies and that much data, this is not a computationally trivial problem to be trying to solve. We're looking at some of the most memory intensive simulations that are run in astronomy, and we're trying to run them over and over and over again. Like we are generating universes 10 to 100 times a day and just expecting our computers to be able to keep up with us and that kind of thing. So the field that I work in particularly is called cosmology, and cosmology is basically the study of how the universe formed, what's happened so far in it, and where it's going to go in the future. So we look from the Big Bang all the way to the present day, and we try and extrapolate that into the future as to how our universe has come to be, what things went into it to make it up, and what happens if we change any of those things. If we change any of the scenarios we're in, can we generate the same universe? And we mainly do this by studying the structures that form. So the big one is galaxies, because they're quite easy to see, but looking at within that stars and black holes and gas and dust. And with all these kind of things taken into account, if you want to think about how many, you know, individual stars, individual galaxies we're forming that all need full physics, that need gas, that need stars, black holes, planets within them, there's just a lot of stuff to be done. And so in cosmology, especially more than any other field of astronomy, we rely on large memory intensive simulations. And actually one of the things that Durham specialises in is these simulations. We're lucky enough to be one of the Dirac centres. So we have Cosma supercomputer, which is basically designed in mind of being able to store all of the data that we need to run these kind of simulations. And this is a great system for us to have, but we're lucky that we are one of very few resources that is a memory intensive compute system. And it's not super applicable if you're not in Durham or not able to access our system to be able to use the kind of simulations that we do. And generally, regardless of what you're doing, if you're an astronomer studying cosmology, you need a HPC cluster. And as the clusters change what they're made up of and as trends evolve, we need to learn to adapt with that. And one of these things is that we now see that there are rising trends towards using GPUs, you know, lots of benefits that I'll go into in terms of like performance and sustainability. But the reality is, if we're going to build lots of GPU-based systems, the people who are using those systems need to be able to use them. And that's part of kind of how my project came about. So I realise probably lots of people know this, but this is the bit that I always go over, so I'm going to do it as well anyway. Just to say that when I talk about GPUs, we're going to talk about them at quite a technologically surface-based level and quite a software-based in-depth level. So all you really need to know on the hardware front is that they are multi-core accelerators that allow us to carry out lots of calculations simultaneously. The analogy that I always give when I present this to astronomers is if you just count the boxes and more boxes is better, you can see you have a clear winner between these two. But that does not come without the caveat that GPU cores are a bit less powerful than a CPU core is, but it means we can put more of them on chip. So if you imagine your CPU is like 4 Olympic bodybuilders and your GPU is 64 guys who go to the gym, if you want to lift a car, you're probably calling the CPU, but if you just want help moving some boxes, the GPU is going to do just fine. So there are some problems that are implicitly more suited to either a CPU or a GPU, depending on what we're trying to do. But more and more, we're trying to find ways to make more of our problems compatible with GPUs. You can see me here. This is my favorite GPU on Cosma. I just thought I should give it a shout out. This is one of our Grace Hopper nodes, which I love very much, and I break on about a weekly basis trying to run things on it. But GPUs are important to us for a number of reasons. In terms of the kind of scientific and technical motivations, we want to get faster runtimes on our codes so that we can do more science with them. Looking forward into the future, we want to look at greener compute. We want better power efficiency and better sustainability in our codes. But also, we want this angle of future-proofing. If we're going to see more heterogeneous architectures, we don't want to leave our code stranded in a place where we can't use or access these. And that's because GPUs do have a lot of benefits. And I think I come from a very biased camp in astronomy where people spend all day talking about how awful GPUs are. So it's sometimes nice to remind myself and other people that they are really great devices and are really useful. We get more floating point operations per second per joule out of them than a CPU. We get really high levels of user control or parallelization, and there's lots of really specific features like using streams or thread block levels or hidden memory transfers that we can only really do on GPU like devices that are actually really beneficial to us when it comes to the software. So if we want the ideal code for a GPU, we want something that is easy to distribute, so no interdependencies, something that is very repetitive, that's going to go over and over and over again, that involves a large amount of compute because we need to offload information to the GPU, run the compute and send it back. So it's a very quick calculation, but needs loads of data. It's not an overall win for us. And things that don't need a lot of memory. And this point especially really clashes with a lot of the things that we do in cosmology because we really do use up every ounce of RAM that we can try and get onto a node. So a question that's been pitched a lot in the last kind of year as they've been looking at, especially the Dirac 4 scoping, has been, if we gave you a machine with 10 times the memory, could you use it? And the answer that's always come back from the cosmology crowd is, yes. Do you have one? Can we have it? When can we get it? Because the reality is, if there is a computer that is large enough to run it, we can provide a problem that is big enough to run on it. Running out of memory is going to be a constant barrier for us until we get to the stage of like unrealistic levels of resolution for us. But the other thing about cosmology codes is there are a lot of them, but they are all quite big legacy things now. So there are a lot of cosmology codes out there that do very similar things, and there are a lot that are in direct competition with each other. But basically every single one of them was designed as a CPU-only code. And in fact, the thing that got codes leverage over one another was how well they could be run on CPU-only clusters. So Swift is one of these cases that I'll explain in a minute of something that was designed specifically to run on the hardware that we had available to us. But now that the shift is going towards GPUs, there's lots of work happening across the field, across the globe, to try and port these codes to be GPU compatible. And that's because we don't have a market-leading code at the minute that can do everything that we want our cosmology codes to do and runs on GPUs. And just from a strategy perspective, this is causing a bit of an absolute nightmare because nobody knows quite which direction we should be going in with our codes into the future. So Swift is the code that I work on. Swift is actually a double acronym if anyone's interested. So it's SPH with interdependent fine-grained tasking, and SPH is smooth particle hydrodynamics, if you are someone who's not kind of done fluid stuff before. So what that means in terms of the code itself is we are a gravity and cosmology SPH-based code. So we use this smooth particle hydrodynamics method to handle all our fluids. It's been around for quite a long time, but it's been the last kind of big public release happened back in 2023. Although it is completely open source and you can go on and see what people are working on in various different areas. But Swift was designed with a more kind of computationally based factor in mind. So it was a collaboration between physicists and engineers and computer scientists at Durham, but also at a few other places to think, let's try and design an astronomy code like we are engineers or software developers rather than astronomers. So the three key principles that Swift runs on is task-based parallelism. So at the start of the run, we make a list of tasks of everything that needs to happen, and then we divide those up across our available cores. Graph-based domain decomposition. So we're not just going to give every core the same number of tasks, we're going to give it the same amount of work. So we're going to weight how much each of our tasks needs to do in terms of the work. And that then we need a lot of communications to make all of this run smoothly. And Swift performs fantastically on large-scale CPU-only systems because when we have lots of cores, we can distribute our work very evenly, and we have lots of things in place to try and stop there being dead time and hang time. But also, we just have a lot of different physics running in Swift. In terms of the variety of science that we do, it's one of the broadest codes that's available in astronomy. So just as some examples, there's 4 kind of examples up on the screen there of different things that we do. So in box A, which is the top left-hand corner, that is a map of the cosmic web that I kind of showed you already. So this is people who are looking at the larger scales of our galaxy, looking at dark matter, which is, substance we can't see and we can't interact with. In box B, you can see gas and dust. So this is like gas feedback from supernovas. So we're dealing with really turbulent gas mixing at high velocities with high energy and forming particles. Down in box C, we have isolated galaxies, so we can zoom in with enough resolution to do a single individual galaxy with the same code that can do the thousands and millions of galaxies that you see in the top left-hand box. And part D is that we do planetary science with it. So the planetary group really enjoys smashing things into planets to see if we can make moons. And they do a lot of this. They've done it for the Earth. They're doing it for Mars now, both to look at how the moons are forming, but also to look at what might happen in terms of the materials and the presence of water and other things like that for potential signs of life. And even beyond this, Swift's been used for some really abstract stuff. There's been like population movement and population control in Nepal was one of the projects run on it. But there is a massive range of science. I put it all on a slide and I realized it filled the whole slide, so I took it out again. But like gas dust, neutrinos, star formation, supernova feedback, black holes, sync particles, entropy, cold gas, ISM, just everything that's like an astronomer's dream toolbox is all within Swift. But it means that there is a massive amount of stuff there that has been written specifically for CPUs. And then suddenly we've come along and gone, let's put a GPU in there somewhere. And you then get the trouble of where are you going to pick, what are you going to target, and what will actually be efficient for this code. So this came down to quite a big question of, do we need a GPU version of Swift? Or do we just want a version of Swift that can use GPUs? And this is the difference between like a GPU rewrite and a GPU offload in our case. So the idea was that Swift is such a massively developed code with so many different areas going on in it that trying to change the entire thing to be GPU compatible was going to be a bit of a lost cause. There was going to be too much stuff to do. And also, if it didn't work, we were going to waste a lot of time and resources in trying to do it. So instead, they picked some key areas that they thought, well, this area is really useful to us as scientists. It performs a lot of the calculations in the code, and therefore we should just try and get this area to be compatible with GPUs, and that's where the kind of offloading comes in. So this project actually started with someone who came before me, who's a postdoc at Manchester, who looks at doing hydrodynamics in this way. And then my PhD came up and they went, okay, well, hydrodynamics is off the table. GPU hydro is going to happen. What do you want to do? And I was just given the free reign of the whole of Swift. And they went, what do you want to do? What's going on GPU, Sarah? So I spent a lot of my first year, benchmarking, profiling, analysing, trying to work out actually what in Swift was taking up time, but also was possible to try and do on the GPU. And I came to the conclusion that gravity was my best friend. So gravity is the one thing in Swift that is always going to be a constant. It's always going to be there. We literally cannot run the universe without gravity. And I've been asked many, many times, if it takes up so much of our time, why don't we just get rid of it? And I have to explain that it is unfortunately one of the very few things that we have to have in an astronomy simulation. But we spend a lot of our time in it. It's utilised in every kind of run. There's always some kind of gravity, whether that's between the particles or with some kind of external gravity source. But also that for our simulations, it was going to be something that was going to be an ideal candidate for GPU because it's an n-body interaction. So that means we have a loop where things are going to interact with each other that's going to repeat over and over again for every particle in our simulation. And that actually, the equations that govern gravity are not that difficult. They're one of the first things you learn in the physics class in high school. You get your Newton's law of gravitation, you get your F equals ma. So realistically, this felt like kind of a low-hanging fruit that we hadn't looked at. And the other great thing is there's a lot of gravity n-body codes out there. that have done things like this already, but none within the framework of Swift and none in the style of system that we were trying to do. So just as an example, this is a kind of pie chart breaking down one of our simulations. This is something called the Eagle simulations, which are kind of large scale structure simulations. And this is an example of Swift recreating one of those simulations. And we spend 2/3 of the time just doing gravity, and then sort of hydro falls on behind, and sort of some packing and some MPI and things like that. But when you're looking at potentially 2/3 of your run and some of your simulations being governed by one equation, that feels like the equation to target a lot of the time. So gravity within Swift is slightly confusing in the way that it's enacted because there's lots of different types of gravity. But what I'm going to refer to a lot today are what we call our task types. So our self-gravity versus our pair gravity. So when we have our simulation box, we take it and we divide it up into lots of cells. And we call a self interaction anything that happens within a cell, and a pair interaction anything that happens between neighboring cells. So for every cell in the Swift simulation, there has to be a self interaction run on it so that all the particles within the cell interact with each other. And then it has to have pairs with as many neighboring cells as it has. And because Swift can recurse its cells, that number can vary from, a few to 27 is a pretty standard one if everything's even, up to like the realm of sort of maybe 80 neighbor cells if something's really overdense and is getting divided over and over and over again. So the range is really massive. But there will always be selves and pairs available for it. So the point of my PhD was to GP offload a section of the gravity calculations. And the idea was we probably weren't going to manage to get everything done in gravity because there's a lot of different functions, but we start somewhere and we see how far through we get. And every time we tick something off, we add another one onto the list. The aim was also to be minimally invasive. So to create the fewest amount of changes to the code and to make this like an option that you could run Swift with a GPU rather than it must be run with a GPU and it's going to be a completely separate code. And the final thing was, it was pretty unclear at the beginning whether this was going to work at all. So it was very much pitched as this is our proof of concept thing. We're going to try this. We're going to let a student at it for 4 years and we're going to see if it works and if it's worth it. Because while I am not the world's most talented software developer, if it takes me 4 years to make progress with this and it still isn't going to do anything useful for us, it's a pretty good case that we need to be looking at other options for this code. So the actual method feels really simple when I write it down or explain it to people, which is that we have all of this Swift code. We're going to take it to be our initial base, and then we are going to write some GPU functions to replace the individual functions within the code. So Swift is written in C, and there was a lot of debate when I started about what language was going to be best to write in. And I want to say this was autumn of 2022 into 2023, and performance portable languages were not as, I guess, widespread as they are now. So things like, I'd never heard the word cocos before. I hear it a lot now. But it came down to, one of my first tasks was, let's write a gravity kernel in a bunch of different types of languages, because we're lucky enough that we have both NVIDIA and AMD GPUs on Cosma. We also have a Ponte Vecchio, but it doesn't work. So there were lots of options of what I could do. So we tested CUDA, we tested HIP, we tested OpenMP, and basically came to the conclusion that the CUDA ones ran best, that we had NVIDIA GPUs available, that we could convert our CUDA into HIP pretty simply with the tools that AMD provides, but mostly that CUDA is quite a well-documented language, and if you're a PhD student that has no idea what they're doing, what you really need is for there to be lots of resources out there to help you with it. So it kind of started writing in CUDA and it stayed in CUDA, it's still in CUDA now, with the exception that we can change it back and forth into AMD compatible forms. Then once we had these kernels and our initial code, you just call the GPU in place of the usual CPU function, and then you do some witchcraft in the make file to make sure that everything links. So it involves a partial compilation. So we have to compile partially with the NVIDIA NVCC compiler, partially with whatever you want to compile Swift with, which can be, Intel or GCC or any of these other things. And then you want to link them all together, and out the other end spits Swift GPU. And when I write it down as 3 nice little boxes, it seems so simple, but it took about 2 years to get it working full stop and get into a position where it would even build the code properly and still manage to run all the science it was supposed to be doing. But we have been in a position now for a while where this has been working and there has been a functional version of Swift GPU. I want to make a clarification at this point that functional does not mean fast. Fast is such a key word with GPUs. So you will go, how much faster is it? How much more efficient is it? We'll come to it at the very end of this talk, but that's really not been a thing that I've been able to focus on a lot. It's not been, is it working efficiently? It's just been, is it working? Is it even doing what it's supposed to do? which I think is quite a common experience if you're a code developer, that you spend a lot of time trying to get it to work so that then once you have a working thing, you can optimize it. But by the time you've got it to work, you're so frustrated at it that you don't even care if it runs optimally anymore. But yeah, so I didn't want to break down my entire kernel, although if you're curious, you're very welcome to have a look at my code. But basically the way that we decided to structure the kernel to try and get the most out of the GPU from just a parallelization standpoint is that each X block on the GPU kernel corresponds to one cell in our simulation. And that means that then we can put one particle on one thread, and the threads are arranged across the Y direction. And then you just look over every other particle. So you hold one particle's information on your thread and you access every other particle's. And that means that you keep quite high occupancy, but also that you can get good amounts of parallelization on it, because you're not having to access data over and over and over again necessarily in the same way. And you just perform as many interactions with the particle that you have as possible. There are lots of different ways that we could do this, and I'm not going to lie, by the time I'm going to submit in 6 months, this might look totally different because this kernel's had about 4 or 5 different versions now. But the general idea is, how do we write something as simply as possible to leverage the GPU's architecture as much as possible for parallelization, as well as just the software itself? So the thing I always get asked first, usually, is people go, well, does it work? Like, can you do the same science? So I always present this plot because it's a nice one for both astronomers and non-astronomers to understand. So if you care about the science side of things, the top half of this plot is something called a power spectrum. So this is a clustering statistic, and it measures scale along the bottom and basically amount of particles up the side. And what it shows is that if you track these over time, you'll see that the distribution of particle clustering, so basically how well spaced out the particles are, changes over time, because when we run simulations, we start to get things like halos forming, we get bits of structure, so we get these over densities. And this is basically a plot to show what does the CPU one look like and what does the GPU one look like. And this is admittedly, I realise, presented slightly strange, but that's because they overlap each other basically perfectly to recreate. So the GPU can recreate exactly what the CPU is doing, which was a first sort of major milestone like ticked off. But the bit that people usually care about is, well, how well is it actually working, which is the bottom part of this plot, which is a relative error between the two. So the grayed out region, that's 1% errors. Where the little dashed red line is, and that's the Nyquist frequency. So that's where simulation resolution of the box is kicking in for us. And we're staying below 1% basically up until our very, very smallest scales, at which point the resolution is taking over anyway, which is like really good in terms of our accuracy and proving that we're managing to recreate what the CPU is doing on the GPU to a very high level of accuracy the whole time. And that actually, with a code like Swift that has parallelization built into it anyway, and so many communications, if you run it twice, it's not going to run exactly the same. So being within 1% error of 2 CPU runs is a normal metric for us. So the GPU managing to be within 1% error was a really good kind of thing, that we were on the right track. I realise plots like this, some people just completely shut down for. So if you're more of a visual person like I am, here is the universe according to CPU and GPU. You're welcome to play spot the difference. The difference is not that one is blue and one is pink, which I have heard a lot. It's just meant to represent the 2 scenarios. But we're basically managing to recreate the same structures. And I realise the colour's not come out super well, so it does look a bit different on the screen. But managing to recreate the same structures with the same kind of densities. And more importantly, we are creating that cosmic web structure in both scenarios. So we're doing the correct science for what we want here. But then, obviously, as soon as we had something that was working, it was then, okay, now we need to get it working well. We need to make it go better. Like, what can we do to actually make this worth it on the GPU? And the problem that we were facing is that there actually wasn't enough work for the GPU to be doing just by sending it one cell at a time. So even if a cell has lots and lots of particles in it, because we have to do a memory transfer onto the GPU to its own memory, we do like a host to device transfer, then we can perform our calculation, and then we have a device to host transfer at the end. If we have lots and lots of data to move into our memory that we need for the calculations, the memory transfer time can take way longer than the actual calculation does if the calculation is relatively short. So the solution that we came up with was, well, we need to give it more work, which means somehow we need to send it more data, but manage to get more work out of that data for the same kind of thing without the memory transfer going so high that we're just completely overruling ourselves. So the idea was, let's send more than one cell at a time. But that means we can reuse all the cells that we send as many times as possible. So let's run, say, a set of 4 cells, and we're going to give those 4 cells over. We run 4 self-operations on them, and we run every possible pair combination on them. And that is kind of how we're going to work it. And this is something that we labeled, I think unofficially, because I don't think it's a technical term, as task bundling. So the idea was that instead of what we had previously, which is that we had a task that was gravity related, we just send that to the GPU, we'd run the kernel, send it back, and then continue on to our next task, that we actually stored and grouped together tasks. And we would wait for an allotted number of the same type of tasks to come by. We would pack them, by which I mean basically we put them into these really long contiguous arrays, just allocating certain particle indexes to certain cells. And then we take all those packed tasks and we'd send it to the GPU, and it would run the GPU kernel on as many of those cells as it possibly could in one go, and then send it back to the CPU. And once we had it back, we would unpack everything and we would sort out all the dependencies of the tasks that we had just been storing. Because when you start to bundle things together in Swift, you have to start keeping track of, is my task actually been done? Has it been completed? Has it been updated? And have we passed that information on correctly to the rest of the code? Because otherwise it either rushes through the code, gets to the end without having done all the calculations, or it just hangs in the middle, waiting for a task that will never appear. So here's an example of what the simplest version of a gravity task dependency looks like in Swift. So right up at the top, we have our initialization and our drifting steps. And then it comes down through a couple of out functions, which are not really important, into basically the three main types of gravity for a very simple scenario that we'd have, which is the self and pair, and then this long range, which is essentially long-term gravity approximation. And then from there, it needs to be passed down to grav down is basically the thing that finishes off the gravity calculations, and then it kicks, and then it moves our time step on. And this is, as I say, the simplest version of this. But you can see that if I went wrong somewhere with the pair grav or the self grav, that's going to ricochet down into our grav down function, which is going to ricochet into our kicks, which ricochets into our time steps, and so on and so forth. So you really need to be quite careful. The other thing is that in a simulation that's a bit more complicated, you also then add some version of some of these things as well. So this is another really common thing. This doesn't have the gravity in this one, but this has all the hydrodynamics and the star formation and the black holes. And then if you imagine that for every feature we turn on, we're going to end up with more of these tasks joining the task graphs, the dependencies get absolutely crazy and they become really like a bit of a bookkeeping nightmare to deal with. So when we then came to dealing with the tasks, there had to be a system put in place for what happens when we pack a task, what happens when we put it into our bundle, but we want to be able to keep our simulation running. So the idea here is that we make our task, we take our task that we want to put into the bundle and we look at its dependencies. And the first thing we immediately do is lock those dependencies. We say that they've not been finished, they've not been completed. We're just going to lock them down and say that they are waiting. We then have all our bundled tasks. We send them off to the GPU. We do the run on the GPU and they come back. And when they come back, all their dependencies are still locked. We're going to keep them absolutely under lock and key so that we can't just carry on through our simulation without checking it. We then unpack the tasks one by one, and here we handle the tasks and their relevant dependencies on a case-by-case basis. So only when we've unpacked one cell can we then unlock all of its dependencies, and then we enqueue those dependencies back into our scheduler, because all of this task-based system is being run by one scheduler who's having to keep up with all of this thing. So for each cell, we go through and we make sure that its dependencies then get unlocked and get put back into the queue. And what that means is we have basically a cycle that goes on and on and on until all of the dependencies are finally met. But there are also lots of kind of other things to think about when it comes to the dependencies, because the tasks themselves also come with locks. And you need to lock down a task before you do anything relating to that task, including just checking what the task is. And then they need to be unlocked so that they're allowed to go and do other things. Things that are locked will never be added to the scheduler, and then your simulation will never finish. Things that are locked and skipped over may then be added to the simulation, but not perform the right science, and we miss a lot of the physics out. Tasks also all have their own counters, where you need to check how many of them you have in a queue, because when we run with more than one thread, we split the tasks up based on their workload. And that means that if we don't keep track of how many of them there are and how many of them we've done, then we risk just missing tasks and stalling entirely. We can also choose to flag tasks as skips, where we basically say we acknowledge that we've seen this task, but for right now, we just don't want to deal with it right now, so just skip over it. And then you can choose whether that means it goes back into the system or it just never gets completed at all. And all of these things come into it when you have the GPU, because what you need to do is put your lock on every task that you want to deal with. You then need to tell the CPU that you've temporarily skipped that task, so that it doesn't keep trying to access it on the CPU and duplicate your work. You need to let the counters know that you've stolen that task. Then you need to run the task itself and manually re-enqueue all the dependencies that come with it. So this whole tasking system took a while to work out, and I was very lucky that people had done similar things ahead of me that I could try and replicate. But this is when people ask about why GPUs and Swift are not friends, and I say the task-based system, this is what I mean by it. The other thing is that if we are bundling tasks up into specific values, that means that we either need to have a perfectly even number of tasks, or we need to have some method for what happens if we have a partial pack at the end. So say I was in a position where I had 15 total tasks left and I wanted to pack them into sets of 8. I'd get one full set of 8 and that would be great, and my code would be like, yep, we've done a pack, let's send all this off to the GPU. But I would also then be left with 7 tasks, which would be hunting forever for an 8th task to fill them in, and there just will never be an 8th task coming. So you need to set some kind of criteria of, if we've packed something, but then we've run out of tasks and we're not going to be able to finish this bundle that we're making, we need to flush this and actually send it to the GPU to still run anyway. And there's a few different ways that you can look at doing this. You can look at the queue and see if you have any more tasks coming. You can try and count how many tasks there are going to be, but we enable task stealing in Swift, where queues can steal from other queues, and then it becomes a bit of a nightmare because your counter is changing constantly. And honestly, sometimes the simplest way is just to get it to check at the end of each iteration. Do I have some tasks left? Do I have any more tasks coming my way? Nope, let's pack them off and send them. The other golden piece to add to this is that tasks can generate more tasks when they have been re-enqueued at the end. So even if I think I'm on my final 7 tasks and I'm just going to send them off, when they come back and I deal with all of their task dependencies, I might generate another 7 tasks from them. So it gets a lot of bookkeeping and admin goes into making this system work. But luckily, I will spare you the pain of going through all of it and just say that it does work for just now, and for that, I'm very thankful. The other thing that we utilize a lot when we're dealing with the GPU is streams. So we can have multiple streams of work on a GPU at once. And currently, I do the most naive version of this, and this is something that's definitely up for being changed across the next couple of months, where we put one GPU stream onto one CPU thread. So across the CPU, maybe we're going to run on 8, 16, 32 threads, and each of those is just going to launch to a different stream. And what that means is that for the tasks that are in that queue that's on that thread, then we can get concurrency in their kernels. So we can launch multiple kernels at the same time and try and get some overlap on the GPU. So it's basically being used as highly as possible at all times. Because the thing with a GPU that actually makes it efficient is that it's only more efficient than a CPU if it's being used really well all the time. It's not just out of box more efficient. So if you have a GPU just sitting there for half of your run, it's still using power, it still needs cooling. It's not actually a more efficient method. So trying to find a way to make sure that our streams are being launched sensibly is really important. And I am looking towards launching multiple streams per thread to get the most occupancy on the GPU. But this is very much we're now reaching the part of the talk where I say everything that I'm talking about now is things that I'm actively doing at the minute, including slides that had to get updated this morning based on what I did last night. So it's very much active development is the key name of the game here. The other thing that I have been experimenting a lot with is what gravity should look like in a situation where we have a GPU. Because currently Swift has 3 different types of gravity. So there's essentially gravity and then approximations that we make around it. And I want to start by saying every form of gravity in Swift is an approximation to some extent, because direct gravity calculations are a massive amount of work to do, even on the world's best supercomputers. So even what I'm referring to as our particle-particle method here, which is the most accurate that we can go, is still an approximation of what true gravity would be, but we're always going to have to make some simplifications in the case of computation. So on the CPU, there's essentially what we're calling our most accurate version of gravity, which is our particle-particle, and then we increase in approximation levels. So we have particle multipole, where one particle interacts with groups of multiples from other particles, and multipole-multipole, where we group on both ends. And the idea is that basically the larger the separation is between our particles, the more we can approximate, because it's not going to matter in the details that much whether we've done a particle-particle or a particle-multipole. So we have things like a multipole opening angle criterion and things like that that help us decide which of these methods we're going to do. And obviously in the current CPU version of Swift, all of this is on the CPU. When I went to start developing for the GPU, I was like, I'm going to start with particle-particle because that one's easy, that one's got loops in it, it's nice and easy to parallelize. Again, low-hanging fruit as a PhD student, you want to take it. But I very quickly realized that the particle-particle bit itself was really simple, but we weren't getting enough work out of it. So I then kind of moved to, well, maybe we can start looking at the other forms of gravity and seeing if we really need them, or actually if when we have the GPU, we can do the gravity in a slightly different way. So the first thing I did was basically scrapped the existence of the particle multipole on the GPU because, well, two reasons. One, particle is quite inexpensive once you get going on the GPU, and we want it to do more work. And part two, multipoles on GPU are an absolute nightmare for us because our multipole structures are massive. They require loads of information, loads of data, and lots of calculation to correctly do the multipole. Whereas the particle, it takes 8 inputs on average, depending on your cell, rather than 8 just to build a multipole to check if we should do this. So it made a lot more sense to just use the data that we were sending anyway as much as possible. And when the computation is as good as it can be on GPU and it's parallelized, it's actually not going to make that much of an overhead difference to us. The multiple approximation got left on the CPU, mainly because it's housed in a completely different part of the code than the main bit that I was messing around with, and also because it's quite inexpensive. It's such an approximation that actually you don't have to go into it in that level of detail. So it just felt right at that point to keep it on the CPU. So then we suddenly realized that we were looking at GPU gravity, not just trying to replicate the CPU, but trying to better the CPU in terms of the science. Like, could we be more accurate? So one of the things that we can measure in Swift is our accuracy against true gravity. And this is a benchmark that we don't do very often because doing the true gravity takes ages and ages to run through the script for. But just an example, this is X, Y, and Z accelerations. So the light blue is the GPU and the dark blue is the CPU. And towards the left-hand side of the plots is basically lower errors. So this is just a small example, just to show that the GPU is managing to get more accurate results to true gravity when we change those particle multipole approximations to particle. And on the kind of level, like you can see the scale of the errors here, and you might say that's a really tiny difference, but that error propagating over billions of particles, looking at exascale size runs that are running time steps, maybe 10 to the 18 particles for 1,000 time steps, small errors start to become noticeable changes in your simulations after a while. And especially if you're doing anything to do with structure formation, we really care about whether the particles are in the right place and whether gravity is operating the way that we think it is. So even being able to show that we were getting more scientifically accurate results off the GPU was give us kind of a bit of a kick that this might actually be something really worthwhile investing into. The big question now at this stage is, do we go all in? Do we just say that there should be no approximations when we have a GPU to do gravity? Do we just get rid of the multipole entirely and run everything directly particle-particle interaction based? Now, there's a lot of case for this in terms of we're already using the GPU, all the architecture is there, the functions have been written, let's pass it over. But the question is this actually enough of a benefit to us? Like, can we balance the transfer times for all of this information that's being sent across if we get rid of all approximations with the amount of GPU work that we're trying to do? Does it start to massively outweigh any of the other areas of work? And also, how does this scale usefulness-wise with our problem size? Because a lot of the test cases that we do for gravity are relatively small numbers of particles. At the smallest test case we do would be sort of order of 250,000 particles in a box. And then sort of jumping up to the area of sort of 6 million. But that's peanuts compared to what we can be doing with these sort of cosmology simulations. And so if we try and do 10 to the 18 particles, and every single particle is going to interact with every single other particle, that suddenly becomes a very large chunk of work. And a lot of the time we put in these approximations to try and avoid doing that. So the question is how much of that we want to undo when it comes to the GPU relations. So where am I currently at? Like, what are we doing right now? Our self and our pair kernels are implemented in the code. Everything bundles, everything offloads. Currently it offloads into 2 separate sets of data, which is not ideal, but I'll come on to that in a second. The big problem I'm having right now is Swift is a great code that likes to make a lot of decisions about what it does. So it goes through and it always looks for the computationally cheapest way to do things. So we have all these trees that say, if this thing occurs, let's do this really cheap operation. Else, if this thing occurs, let's do the next cheapest operation. And then suddenly, the second that you start to put in things like, let's skip this type of gravity entirely, or let's replace it with something else, those decision trees and how we handle them start to become a bit more difficult, because not only are we dealing with looking at how, say, 2 cells interact together, we're having to pick every combination of the 2 cells that we've sent as part of our bundled up pair, which then becomes a lot of bookwork on the CPU side. And really the CPU-GPU balancing act is not just how fast does the code actually go when it's on the GPU, it's how fast does it go when we take into account all the other stuff we also have to do to get the GPU working. So the conclusion that I've come to in the last 48 hours is we're about to have another restructure. Luckily, it's just going to be mostly a copy and paste and drop job across some of this. That's going to mean that hopefully our decision trees are called a bit earlier in our process, so that we're not packing things unnecessarily that we then need to unpack later, while also hopefully getting as many direct particle calculations going as I can manage. The kind of other big thing that I'm looking at right now is how this will all fit in terms of storing information about all of our cells. So we have these, long arrays of packed cells that we need to know everything about at one time. We have all their dependencies and all this stuff. But the then question becomes, how do I use these packed cells as efficiently as I possibly can? Because right now, self-tasks and pair tasks are completely separate in Swift. So if it gets a self-task, it packs, and it tells me that's a self-task, and it packs 8 self-tasks together and sends those. And then it takes pair tasks and it packs 4 pair tasks, because each comes with 2, and sends those instead. Whereas actually what I want is to get a position where we have packed 8 cells, and then we do as much work on those 8 cells as possible, which would involve fundamentally changing the way that our bookkeeping and our task scheduling happens. Because it would mean that as default, whenever we sent a cell, the first thing we would try and do on it is calculate its self-gravity and then make every possible pair combination. But that overrules the task scheduler, which then would need to be updated in hindsight. And this is going to cause a fair amount of overhead anyway between our CPU and our GPU. But more importantly, if we have a multi-stream version where everything is trying to do that to every combination of cells it's got, you end up with a logistical bookkeeping nightmare. So this is very much something that's in the conceptual regions of my brain, and maybe not something that makes it into the thesis, but something that makes it as a thought experiment at the end of the thesis of how might we do this if you could afford to have someone spend another 4 years working on this kind of particular area. There's also a lot of considerations that come with this, and the more discussions I have with people, especially people who are in computing, the more of these I realise that as astronomers we really just overlook entirely. There's some things that we're very aware of in our simulations because they affect other areas of our simulations, but we don't really think about how they affect the compute that our other areas of simulations are doing. So things like, how big should a cell be? Currently, my cells are order of 10,000 particles big, which is a really good number for me because I get loads of information from the GPU on it. But hydrodynamics wants particles to be 100 to a cell. Star formation wants particles to be 50 to a cell. So how do we find either a method that unites these together? Do we add a recursion within our cells for certain types of science that we're trying to do? Or do we just settle that cell size is going to be a particular thing? Also, who gets to decide how big the cells are? Is it set based on the problem that we give it, based on the data input that it's reading in as its initial conditions? Is it something that the user decides? Is it something that should be hard-coded as a limit because we always want it to be the same? Currently, I have it as a user choosable parameter, so the user puts it in as part of their parameter file, and the GPU then, we read information from the GPU about what type of GPU it is, how big it is, how much memory it has, and it basically takes the problem size that the user's given it, the GPU memory, and divides and automatically works out how many cells it could sensibly pack into things. But this is a very floating question, how many should we be packing? Is this something where the user should actually get to decide? How easily could a user break it if they chose a really bad number? Also, things like our threads. How many threads do we want to be running on the CPU? How many streams do we want to be running on the GPU? How much do we want to change that to affect our GPU occupancy, realizing that that's going to have a ricochet effect onto every other task in Swift as well? And from a physical perspective, how does the code perform in really uneven and unusual situations? So in cosmology, we love clumpy things. We love when gravity pulls things together and we get lots of little over densities. But that means that some of our cells might have 1 particle in, and some of our cells might have 10,000 particles in. And that kind of uneven distribution is not great for parallelization either. So there's a lot of different, I think, thought experiments that are being performed. And every time I sit down and have a meeting, more and more of these questions come out. And a lot of the comebacks that we come to are just, let's try it and see, let's profile it and see, let's time it and see, and let's work out what's going on. Performance. I promised I'd come to it right before the end, just so we can go over this. I'm going to be totally upfront and say I do not have an end-to-end speedup at this point, which I know is the thing that everyone wants to know about in GPUs. But I don't have one because the code's not finished, and I don't want to give you a wrong stat. At the last version of the code that was fully running, the GPU version was about 20% slower than the actual version without full science integrated. So the number changes constantly. A few months before that, it was 40 times slower. So one thing it's not at the minute is any way faster. The calculations themselves, though, are definitely faster. And this says order 4 times. I think it's actually technically something like order 6 times faster now. But for GPU world, that's actually not that good. You know, people want 10 times faster or more really on a GPU. But this is, again, now we have the framework set up, the optimization becomes a different problem than actually getting everything into place. The transfer overheads are the main issue because we have to count those in with the GPU time. If we just look at the calculation time, it looks great. But when you actually consider that you have to do packing and unpacking and transferring and bundling and all these extra things, the performance just generally becomes a little bit worse. I will say on the hydro side of the code, they have some really good performance indicators. Abiz and Hazar wrote a great paper, which I can point you to if you're interested to learn more about what they've been doing. But it makes me hopeful that maybe we can do that with this as well. And every time I develop something, it does close the gap a little bit, which is exciting. The aim is that hopefully by the end of September, when I need to submit my thesis and release this code into someone else's hand, that we'll have about an equivalent runtime in code. And I honestly think that if we get that, that's an achievement in itself, because there's just been such a massive job to try and make this in any way compatible. And it does at least mean now that we have a GPU compatible version of Swift. I'm very much of the opinion that future work to optimize is way easier than future work to finish an implementation of something, because someone else could take my code now and look at it and make it better. But only, as my mum would say, only the Lord and I know what went into that code in the first place. So it's quite important it gets finished. The other thing is, it would be absolutely huge if I had enough time to document all of this in a proper way, and I'm trying to do it really badly, but the strains of publishing and trying to get results out is massively outweighing the quality of coding that's currently happening, I will say. So in terms of my next steps, I say I've got a few months, and I will be working on this probably up until the thesis is submitted and just updating the thesis accordingly. But a lot of stuff to optimize the cell looping and the bookkeeping for the gravity, thinking about pack sizes and threads. And then the other thing that I would love, even as a test case, to try and get done is a multi-GPU application. Because right now the framework is in place that it could offload to any number of GPUs. It's just that at the minute it doesn't. It just offloads to one and splits that one as well as possible. But for lots of bigger machines that have multiple GPUs per core, it would be really, really great to multiple GPUs per node. It'd be really great to try and get a multi-GPU implementation running, and this is something that they have managed to do with the Hydro code as well. So I'm hopeful again that that's going to be the case. So some key kind of takeaways. We need GPUs in Swift so that we can actually survive into the future. We have good results for accuracy. Speed up results are a bit more tenuous, and hopefully I will manage to get there in the end. Just to say again, thank you so much for having me and for listening. I'd love to discuss my work more, but I also, as some of you have experienced, would also love to hear about your work. I would really love if you tell me about what you work on, why you chose to do RFC work, and any other general advice, because the job market is a scary place and I would like to know what I'm getting myself into. But yeah, thank you so much.